Hi, welcome to Physics with Ben. Don't forget to hit the subscription bell and also subscribe for more educational contents. In today's class, I want us to look at refraction of light through biconvex lens. Yes, in every experiment, there is what we call the theory of the experiment. Without the theory of the experiment, you won't understand the experiment. So I want to encourage you to click in the description box below to find the video link on the refraction of light through biconvex lens, through concave mirror, through plane reflecting surface. I have done all of those videos. You just find them in the description box below. In today's class, I want us to know some simple, basic, hidden facts in refraction of light through biconvex lens. The biconvex lens is a lens that is described as follows. The lens is thick at the center and thin at the edge. It is thick at the center and thin at the edge. The rays of light, after refraction through the lens, they converge at a point. So this experiment is going to take time. I want to teach us how to do some simple stuff, how to measure focal length, how to measure our object distance, how to measure our image distance. These are the simple stuff the examiners would want you to do when you are asked to perform experiment in this topic. I will also teach us how to measure the magnification of the lens and also how to measure the converging power of the lens. And then what you are supposed to do is that these processes are repeated for some given number of variables. For instance, before we dive into the lesson, I would love to explain some stuff before we continue. Now, this is the lens. It is called biconvex lens, meaning it has two faces, one this side and one the other side, biconvex. So the distance from the pole or the center of the lens to the ray box is actually what we call the object. You can see the illuminating object here. There is a nail here, and the nail is upright. And if you look at the nail appearing in the screen, on the screen, the nail is appearing upside down. We call this the image is inverted. So the distance from where this lens is to the ray box here, we call it the object distance. And we denote that with a U. And then the distance between the lens to where the screen is, we call it the image distance. So having the information for the object distance and the image distance gives you an idea on how to calculate the focal length of the lens. I forgot something very, very important. I'm going to teach us how to measure the object height and also how to measure the image height. And then we're done with the experiments. So before we continue with the experiment, it will be very important for us to recall the equations that are used in this experiment, or let me say, the equations that are controlling this experiment. And one of the equations is that is given as your R is equals to 2F. We call this equation number 1. We also have the general lens or mirror equation as 1 all over F is equals to 1 all over U plus 1 all over V. Let's call this our equation number 2. We also have another equation given as the magnification of the mirror or the lens is given to be M is equals to image distance divided by the object distance U. Magnification is also given to be, let's call this our equation number 3. Magnification is also given to be M to be equals to image height, I write it IH divided by the object height. We call this equation Number 4, we also have the power or the converging power of the lens, and this is given to be P is equals to 1 all over F. We call this our equation number 5, and that is measured in the units of Daltons. These are the simple basic equations that can be used in this topic, or that are used in this topic. So without wasting more time, I am going to outline the parameters that we are going to measure in this experiment, and I will guide you on how to measure them and how your table of value will look like, and then we'll call it a day. For us to run this experiment properly, I would love to introduce to us the apparatus needed for this particular experiment. First up, you need a power source. This is my power source. Very, very important. My extension cable. Number 2, you need a ray box. The ray box is an illuminating object. It stands as the object. While if you watch the video, I asked us to watch in the description box below, you will hear terminology like objects, object distance, object height. So this ray box is acting in the capacity of our objects. If you look very well, I drew a line here. This line is not drawn there for fashion. During the measurement, the 0 point on my ruler will have to align with this line, and that is where the object is. Thank you. So the next thing you need a measuring ruler. This is a meter rule, meaning 100 centimeters. Number 3 is you need a lens holder. This is your lens holder. The lens holder also, I did the same thing I did on the ray box. I drew a line here. This line is standing as the line of symmetry, passing through the center of the lens, or the center of curvature of the lens. So while measuring, this ruler, the 0 origin or any number that I want to take in consideration, must align with this line here. Yeah, you can see it now. This is the line I am talking about. This is the line. So the measurement must align with that line. And then for this number 1, 2, 3, 4. So number 5, you need the lens. This is the guy without which the experiment cannot be performed. We call this the biconvex lens. Some people call it convex lens. I am not too comfortable with that because this guy has 2 sides, one side and the other side is, so it is called biconvex lens, not convex lens. It is called biconvex lens or converging lens. Biconvex lens in the sense that it is the shape, and converging lens what the shape does. It is converging lens because after refraction of the rays of light through the lens, the rays will converge at a point called the focal points. This guy also is used in new technology to heat up stuff and to cook. We'll look at that another day. Last but not the least, you need a screen. I constructed a screen today because sometimes the screen will have to capture a very wide image, and if the screen is not wide enough, this is what I used to have in those days. Let me show us quickly. This is what we have originally in our lab. This one cannot contain bigger images, so I have to improvise for this one, and this one can capture any large image. So this is our script. So without wasting more time, let us go straight to the business of the day. The next point I want to discuss now is very, very important, because this point will help us do the experiment properly. I'm making this video because of this year's WAEC examinations, Physics 3 examinations. Everything, if you are watching this video, and also the video links in the description box, and this experiment happens to show up this year, I bet you're going to get your 25 over 25. Good. Now, when do you take your readings? Very, very important. You can only take your reading when you see a sharp image displayed on the screen here. And anytime an image is displayed on the screen, we call it a read image. Read images are those images that can be captured or displayed on the screen, while the virtual images are the images that cannot be captured or projected on the screen. So right now, you can't take any reading. The lens is placed the lens is placed in between the red box and the screen. This is our screen. So while doing the experiment, you are given various distances from the object to the lens. We call it the object distance. From where I drew this line to where this line is drawn on the lens holder, we call it the object distance, U. Good. So you could be given values of U like 20 cm, 30 cm, 40 cm, 50 to the number the examiners would want you to measure. And then you have to measure your object, your image distance is from here to here. But before you measure your image distance, you must be sure that the image on the screen here is very sharp. And that is precaution number 1. Precaution number 2 is that you also avoid error due to parallax. Error due to parallax is the error avoided while using measuring instrument. In this case, our measuring instrument here is the meter rule. So you can state these precautions as follows. I ensured there was a sharp image on the screen before I took my readings. Number 2, I avoided error due to parallax when taking reading on the meter rule by looking down straight. You can't stand like this to take your reading. You can't stand like this to take a reading. And so when you look vertically down straight on your meter rule, you are avoiding that error called error due to parallax. Error due to parallax, I repeat again, is the error avoided due to the usage of measuring apparatus. When you are measuring, doing experiments under electricity, you use measuring apparatus like the ammeter, the voltmeter, the galvanometer. So when you are taking reading on the ammeter or the galvanometer or the ammeter, you will state as follows the precautions. I avoided error due to parallax while taking reading on the ammeter, the galvanometer, and the voltmeter by looking vertically down straight. In this case, the meter rule here is what we are using. So we can state the precaution as follows. I avoided error due to parallax while taking reading on the meter rule by looking vertically down straight. Number 2 precaution that gives you an edge over the experiment is this. Right now, I'm going to place the lens at an arbitrary distance. And while doing this, you don't touch the lens. What you touch is that you adjust the screen. You keep adjusting the screen until when you see a sharp image, then you stop. So let's see what I'm going to have. Okay, let me put it this way. Okay, observe what I'm doing. You can't take any reading right now because you cannot even see any image. So here, there's no image appearing. You take it back. You take it back. Keep moving it. Good. You can still see the logo on the bulb appearing right now. Keep taking it back. Keep taking it back. You can see the nail. You can see the nail, the object. This is the nail. You see that? That is the object. The nail is upright. It will appear inverted on the screen. So you just keep observing what I'm doing. So you keep adjusting. You see the nail is showing up. The nail is showing up. It's showing up. Good, good, good. You can see the thread on the nail. So at this point, you are going to take your reading because the image is sharp. And again, the screen will not be like this. The screen should be perpendicular to the ruler. I take that again. The screen should align perpendicular to the ruler. Then you take your reading, not at any inclined angle like this, but the screen should be perpendicular to the ruler. And then the image should be sharp on the screen. Then you take your reading. When you maintain these 2 rules, these two, when you maintain these two rules, or let me say precautions, then you're going to have a very, very perfect experiment. So having looked at all of these things, let us go straight to the business of the day. This is what examiners do. The reason why I resolved to have a ray box of this nature is this. I have other ray box who are not of this nature. I love using this one because sometimes the examiners may ask you to measure the diameter of the hole. So for the diameter of the hole, this is what you do. You use your divider, you measure it like this, and then you transfer the reading on a ruler. You transfer the reading on your 30 cm ruler. Good. So you can see the nail inside that. So there are two things involved here. It is either we are going to measure the diameter of the ray box, or we are going to measure the height of the object. So this is our object's height. You see what I'm doing? You measure it this way. So object height O subscript H. So I am going to transfer my reading on the ruler now. Let's see what we have. Good. So this is the calibration on my 30 cm ruler. It is not too bright, but you can manage with me. Good. So what you do is that you transfer the reading. As you can see, we are having 0 to 1, that is 1, 2. We are having 2.5. Our object height is 2.5. And so we record 2.5. These are the parameters that we are going to measure in this experiment. And so this is for our object height. It is 2.5. So we have 2.5 centimeter. We are done with that measurement. Next up, I am going to align my ruler with this line here. I am going to align my ruler with this line. So I am doing that right now, and this is it. And then I'm going to place the lens holder with the lens on top at 20. You should push the lens not to be close to the ruler, but a little bit far away from it. So we're going to use this to align the measurement. So the lens is at 20, and this is the arrangement. Right now, we have chosen our object distance to be 20 cm. The object distance is what examiners always give in the exam, while you measure the other ones by yourself. So our object distance U is 20 cm. Good. Now I'm going to take the camera close so that you see the setup for the arrangements. So this is what I'm talking about. Your ruler should align with this line. That is your objects. So from this point to this point, we call it the object distance. From 0 to 20 is the object distance. And then from this point to another point here is the image distance. This is our screen. This is our screen. You can see the arrangement from this angle. Good. So our image distance can only be determined when we see a sharp image formed on the screen here. So right now I am going to plug in the power source, and see what will happen. So I'm going to adjust this. I'm going to adjust this until I see a sharp image. I'm taking it further away. Is that image sharp enough? Look at it. This is a blurred image, not sharp. Let's take it back again. I think this is sharp enough. This is sharp enough. So at this point, we can take our reading. So I brought it very fast so you can see it once again. Good. So from the ray box to here is our object distance, and that was 20. And from here to where the image is formed very sharp is our image distance. Let us take our reading right now. So let us come close. This is from 0 down to what? Good. You can see that the ray box, the screen is perpendicular to the ruler, and the point at which this perpendicularity takes place is the point of this perpendicularity is good. You can see that the point at which the ray box, the screen, is perpendicular to the ruler is 84.5.6. 84.6 is the point. So 84.6 minus 20 gives us our image distance. So 84.6 minus 20 gives us our image distance. That is 64.6. So write that our image distance is 64. Our image distance is 64.6 centimeter. So now that we have our object distance and our image distance, we are going to apply the general lens or mirror equation, which is 1 over f is equal to 1 over v plus 1 over u to find our f. So having plugged in our equation, this is the result on ground. 1 over f is equal to 1 over v plus 1 over u. And if you make the focal length of the lens the subject of the formula, you have uv all over u plus v. You plug in the equation, you evaluate, and then the focal length of the lens is approximately 15 cm. Good. So this is a useful and very, very important information for physics teachers as well. Sometimes you will go to the shop where they are selling physics apparatus, and you will tell the market dealer that you want lenses or focal length 15. Focal length 15 is what we always use in WAEC. This will help us as teachers as well. Sometimes when exam comes, the WAEC blueprint will specify that you should use a lens of focal length 15 cm. As a teacher, how do you know that? There are other ways of knowing this, but this is one of the ways. How are you sure that what you are using is 15 cm? Because sometimes a focal length of 30 cm is placed into a label of 15 cm. You bring it and you'll be working and you'll not be getting your result. You think that what you are doing is wrong. So this is how to test if the focal length is truly 15 cm, is actually what is written on the label or not. There are other ways of finding it. You can make research about that. For the sake of this video, this is how to find the focal length of the lens. So we are moving forward. In summary, from here to here was our object distance, that was 20. From here to here, our image distance, that is 64.6 cm, and then our focal length is this. It means that a distance from from the lens a distance of 15 cm to the center of the lens, the rays of light will converge at the other points. And that point of convergence, if it is the rays of sun that is passing through here, if you put your hand, you're going to feel a painful sensation. If the surface area of this guy is very wide, then whatever you put behind him will be set ablaze. That is why this guy is used in renewable energy in this generation to generate a lot of heat for cooking. So let us proceed to measure the other variables in the experiments. The next variable we want to measure is the radius of curvature, R. The radius of curvature has a relationship with the focal length as follows. R is equal to 2f. So we mean that 2f will give us R. So our R is 30. So you write 30 cm here. 30 centimeter. Good. As simple as ABCD. The next parameter I want to measure is the image height. So we'll go back there and plug in a ray box to illuminate there and measure the image height. The same way we measure the object height is the same way we are going to measure the image height. So we are going to use this guy to measure our image height. Observe what I'm doing. Good. So you can see that the image is magnified. The image is magnified. So we are going to transfer the reading on our ruler here. Good. So from 0 to this point, what do we have? That is 8.1. So we are going to record our object height as 8.1. We record 8.1 cm. That's our object height. Good. The next step, we're going to measure our magnification. Because we have gotten our V, our U, our OH, object height and image height, we are going to calculate for our magnification of the lens as follows. I hope you recall this set of equations. Magnification has two equations, V over U or image height over object height. Magnification is a dimensionless quantity. It has no SI unit. So we're going to use this equation 3 and equation 4 to find our magnification. Thank you. So having plugged in the equation for magnification, this is our result. The magnification is given as image distance over object distance. We plug in, we got 3.23. I told us magnification is a dimensionless quantity. So as a physics student, if you calculate and you put the SI unit, they will mark you down. Look at this result. We use the other results, the other equation, image height over object height. We got 3.2. So to the nearest whole number, we have 3. And to 1 dp, we have 3.2 and 3.2 each. So this proves that our experiment is very, very perfect. We're not going to stop here. We proceed to measure the other variables. So we're going to record our M to be 3.23 or 3.24. So these are the variables that we have measured so far in the experiment. The next thing we want to measure is the converging power of the lens. The converging power of the lens has a mathematical relationship with the focal length of the lens given as P is equal to 1 all over F. So the converging power of the lens, while calculating for it, the units for the converging power of the lens is in diopters, with capital D, diopters. So while calculating in diopters, you have to convert your focal length to meters. And that is exactly what I did here. So 15 divided by this, we got this, and this over this. So it is the inverse of meters, or capital D. This is the unit for the converging power of the lens. Next up, I am going to show us a template table of values of this particular experiment, and then also the ray diagram for this particular setup. So what you will be expecting in your exam is that examiners are going to give you different sets of U's, that is object distance, varying from 20 maybe to 100, 20 cm, 30 cm, 40 cm, 50, 60, 70, 80, maybe 90 cm. And sometimes you may be asked to repeat what I just did here for like 5 times. And that is what we call the experiment in refraction of light through lenses. So in conclusion, this is the optical ray diagram for this experiment that we just did. This is the ray diagram. I have made a video on how to construct or draw ray diagrams. Just click in the description box below and you see a step-by-step approach on how to draw a ray diagram. By the way, before I conclude, let me just do a quick recap. While drawing a ray diagram, the first thing you need to do is to draw your principal axis, which is this line. The next thing, you have to draw a perpendicular and then use a protractor to draw your lens. While drawing that, make sure that the distance from here to here is the same as from here to here, and the distance from here to here is the same as from here to here. Now, your center of curvature is at the center of the lens. So the rays of light are coming from this end. While doing that, the distance from the center of curvature to the focal point here should be the same to 2f. That is, if you are taking from here to here as your 2 cm, from here to here too must be 2 cm. From here to here must be 2 cm, and from here to here must be 2 cm. That is the secret involved in drawing the ray diagrams. So we have used 3 of the rules governing ray diagrams here. This is rule 1, rule 2, and rule 3. Before you draw a ray diagram, you need at least 2 or more rules. The number of rules that you are going to use are strictly determined by the position of the object. Sometimes the object is placed in a place in such a way that you can only use 2 rules, but you can't use only 1 rule because the 2 rays must intersect at the other side, hence the formation of the image. Sometimes you draw this and then the rays don't intersect. We say that the image is formed at infinity. You can watch the video in the description and know of all of these things. So this is the ray diagram. The ray diagram is a perfect representation of the experiment. You can screenshot this and study it later. The next thing I want to explain, but before I explain that, from here to here is a focal. This is the focal point, and this is another focal point on the other side. So from the focal point to the center of curvature is the focal length, and it is 15 cm or 0.15 meters. And then from here to 2f is your radius of curvature, which is represented. And your radius of curvature is 2f, and this is what we had even in the experiment. And then your u is up here, the object distance 20 cm, and then the image distance 64.6 cm. And then the power of the lens, which is this. Next up, I want to show us how a typical table of values for this will look like. What we did, this is the full representation of it. The focal length is a constant, so it is recorded on top of the table of values. It was 15 cm, you have to record it 15.00 cm to 2 decimal places, or you lose your mark. While doing this experiment, you record all the constant on top of the table of values. So the focal length is a constant for a particular lens you are using for the experiment. It does not vary. So if you are using different lenses, they have different focal lengths. So I can't record my focal length. You can't record my focal length in your table of values, except if the focal lengths are of the same size. The radius of curvature is also a constant for a particular lens, and it is 30, so it is on the top. The object height, which is this, is also a constant for a particular ray box. It is on top of the table values. And then also the converging power of the lens is also a constant. So our U was 20. See how we recorded in the table of values. 20.00 cm. That is how it should be recorded. Our image distance was 64.6. We have to record it as 64.06 cm. See, we record all of this to 2 decimal places. And sometimes examiners may ask you to find U inverse and V inverse. And then the magnification, which has no unit, and that is how to go about it. The reason why you will be asked to find this, and this is that you'll be asked to use the mirror equation 1 over f equals 1 over v plus 1 over u, and then you have to make 1 over v the subject formula. In that case, you may be asked to plot a graph of 1 over v on the vertical axis and 1 over u on the horizontal axis, where -1 is the slope and 1 over f is the intercept. To this, I think we have come to the end of these experiments. Now, this is what you may have in your WAEC exam this year. So, you can even repeat these values. So, you may be given other values of u as 30 down to this level. Then, before I conclude this video, I want to shock you that, do you know that at this point, you can perform this experiment without coming here? If you know how to go about it, drop your comments in the comment box. There's a way you can do this experiment now that we have all this measured. We cannot suffer ourselves by going back here and trying to adjust the screen throughout the experiments. It is an experimental hack I teach my students only when they're about to graduate. If you claim you know the secret, drop it in the comment box and then we'll chat me up. To this, we have come to the end of this experiment. And as usual, I wish you guys all straight A's. Thank you, and God bless you. Bye-bye.